Hi everyone, and welcome to this video. In this video I want to go over systems of linear equations, kind of show you how it works, and in the next video I'll do some examples for you. So let's start. Let me share my screen with you. All right, systems of linear equations. First of all, let's talk about linear equations. We have seen this, you have probably seen this before in two dimensions. When you write a linear equation in two variables, you can write that as a1x plus a2y equals to b, or just ax plus by equals to c. This is the equation of a line, and once you isolate it, you can get the slope and the y-intercept. We're not going to do that here. I just want you to see it works the same way. When we are in three dimensions, you can write a1x plus a2y plus a3z equals to b, or just simply ax plus by plus cz equal to d, and that's the equation of a plane. And if you go more, you can write in n dimension a1x1 plus a2x2 plus dot 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 anxn equals to b. Now let's go over some definitions. B here is the constant term. A1 is the leading coefficient and x1 is the leading variable. A little note here, how you can write the parametric representation of a solution set. For example, if you have this equation and you know this is a plane, we can just let y and z to be the free variables. And remember this term because throughout the course we're going to use this a lot. So in this case, we just let y and z. You can let x and z or y and x to be the free variables. It doesn't make a difference. But let's see how the notation changes. If there are free variables, that means we can write them as parameters. So parameters are just letters. So z, okay, we can say z equals to t and y equals to s. So if we substitute, we get 3x plus 2s minus t equals to 3. Or then go ahead and isolate x. So take 2s and negative t to the other side. And you can divide by 3 both sides or every single term. So you can write x as negative 2s over 3 plus t over 3 plus 3 over 3, or simply negative 2s over 3 plus t over 3 plus 1. Now the solution can be written as 1 for, so the first number is x here. So this is x, which is 1 minus 2s over 3 plus 3 over 3. So all I did, I just wrote that one. And we called our y to be s and our z to be t. And I put a note here for you. This is the vector presentation. So just be patient. We're going to see that in the future lectures. Now, systems of m linear equations and n variables can be written like that. So the first equation is a1 1x1 a1 2x2 plus dot 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 a1 and xn equals to b1. A1 in the second line, a2 1x1 plus a2 2x2 plus dot 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 plus a2 n xn equals to b2, and so on. So the last line you can write that as am1x1 am2 x2 dot 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 and plus amn xn. So as you notice, what we have here is m equations and n unknowns. So this is an m by n system of linear equation. Just to get you familiar with this, if you want to write the matrix notation, this is called the augmented matrix. In the next video, I'll talk about this more, but you don't write the variables. So the this is the coefficient matrix, and this is the constant matrix. So A11, A12, dot, 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 A1n, and so on, A21, A22, dot, 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 A2n, till the last line is AM1, AM2, AMN. And of course, the coefficient matrix, the constant matrix, we know that it's an m by 1 matrix because we have m rows and n and 1 column. So just to refresh your memories of systems of equations, of 2 equations and 2 unknowns. So we have seen in algebra, it's ax plus by equals to c dx plus ey equals to f, or simply if I change notation, they're exactly the same thing. A11 x1 plus A12 x2 equals to b1, A21 x1 plus A22 x2 equals to b2. These are, each equation is the equation of a line. So what can happen to 2 lines? Either they cross each other at one point, so they intersect each other, or they're just one line, they're the same line, they coincide, or they are parallel, they never cross each other. So that's what we can get with 2 lines. In summary, when that happens, when number 1 happens, then we have one solution or a unique solution. When the system and the lines are the same and they touch each other everywhere, like case 2, then we have infinitely many solutions. In both cases, the system is called to be consistent. The third one, the lines are parallel, they never intersect, so the system has no solution, or we call it it's inconsistent. Now, to solve a system, there's some operations we can do and produce equivalent systems, and it's good to know those. One is interchanging 2 equations. When you interchange 2 equations, nothing happened to the system. You are going to get still the same solution. You can multiply an equation by a non-zero constant. Or number 3, you can add a multiple of one equation to another equation. A simple example of that, if I start with this system, so what I can do is interchange equations. So basically 2 becomes on the top and 1 goes below, but it's still the same system. I can take the first equation and multiply it by a constant. Here I chose 2. So you get 2x plus 2y equals to 6. Multiply that by 2, and the second equation stays. If you solve this system, you're going to get exactly the solution of that system. Number 3, you can just multiply the first equation by 1 and add it to 2, and that's the third operation here. So if I do that, so it's just basically just add them. X plus x is 2x, y minus y is 0, and 3 minus 1 is 2. So you can write the system as x plus y equals to 3 and 2x equals to 2. This system is going to be the exact solution of the previous one. Now, if we want to solve this system, in algebra, we learned we have the very 2 common methods. One is substitution and the other one elimination or addition. So here I use elimination. If you want to solve this system, basically you can add the equations because we know the y variables, they have the same coefficients but the opposite signs, so they're going to cancel. So x plus x is 2x equals to 2. Isolate x by dividing both sides by 2, so you get x equals to 1. Next, you can eliminate x, or you can just substitute. We have x, you can go to number 1, and x is 1. We found that 1 plus y equals to 3. Isolate y, and y equals to 2. So this system has a unique solution, and that's the point where the 2 lines, if you graph 2 lines, are going to intersect. Now another example here I put for you is a 3x3 system. So we have x minus y minus z equals to 0, x plus 2y minus z equals to 6, 2x minus z equals to 5. One way of doing is, there are several ways, but one way of doing is you can pick 1 and 2 and eliminate a variable there. I decided to eliminate x. So you can multiply 1 by -1. So you get negative x plus y plus z equals to 0. And number 2 is x plus 2y minus z equals to 6. So if you add them, you get 3y equals to 6. Divide both sides by 3. So x is solved. This one was good because once we did that, we eliminated the x and the z. So now once we have y, we can pick number 2 and number 3, and try to eliminate the same variable you eliminated when you took 1 and 2, and that was x. So what I did, I multiplied the first one by -2, so you get -2x minus 4y plus 2z equals to -12. All these numbers you multiplied by -2, and 3 is 2x minus z equals to 5. If we go ahead and add them, so x's cancel, the term with x is canceled, and you're left with -4y plus z equals to -7. We have y, you substitute, so you get -8 plus z equals to -7, isolate z, and you get 1. So we have all three of them. So the way, again, this system has one solution or a unique solution. These are 3 planes intersecting in one point, and the coordinates of that point is 3, 2, and 1. Then I have another one here for you. Same way, x plus y plus z equals to 2, -x plus 3y plus 2z equals to 8, 4x plus y equals to 4. So I picked 1 and 2, and I decided to, since the third one doesn't have a z term, so here I decided to eliminate z. So if you multiply this by -2, so you get the first one by -2, you get -2x minus 2y minus 2z, and number 2 stays the same, -x plus 3y plus 2z equals to 8. And if you add them, so you have -2x, -x is -3x plus -2y plus 3y is just y, and you're left with 4. So we can call this number 4, and we can put 3 and 4 together, 3 from the original equation and 4 the one that we found. And this is just 2 equations, 2 unknowns, and you can solve for x by just multiplying the top one by -1, so you get -4x minus y equals to -4, -3x plus y equals to 4. This is -7x equals to 0. Solve for x, and x is 0. You can go ahead and substitute the value of x, which is 0, in number 3, which was right here, and so you get 4 times 0 is 0, so y is left to be 4. And you can go to number 1, substitute x by its value and y by its value, and solve for x. This is also a unique solution, and you can write the solution like this for now until we get to vector notation. So x is, we have x, y, and z. I think that's it for this video. In the next video, I'm gonna choose more examples, solve it for you, so you can then pick examples from your book and do it and finish the homework. Thank you, and I'll see you in the next video.